Last week we begin the lecture number 6, and today we finish the lecture number 6 and in the first part of the lecture number 7. And so the lecture number 6, that is about the linear transformation. And also I tell you something about the mapping, and give you something about the mapping and what is the linear mapping. Mapping, or you can call it transformation. And it is here a function of mapping, that is a map from V to W, where V and W are vector space. And in that case, V will be called the domain of T, W the codomain of T. Hai bạn thế giới kìa, nghe anh là thôi à? Các bạn không có mic mà nói còn to hơn cả tôi à? So here is some name about that. The mapping is some corresponding from V to W, and the V will be called the domain and W the codomain. Now we have the name of the image of an element V, something like that. And in that case, V will be called the brain image of W. And usually, each element in the codomain will have several brain image. And then we define the case when a transformation will be called linear. It will be called linear if it satisfies two properties like that. And because of that, it is said that a linear transformation is a mapping which preserves operation. Preserve operation means it preserves addition in V and scalar modulation in V. It transforms addition, vector addition in V into vector addition in W, and it transforms scalar modulation in V into scalar modulation in W. Next, we have the four properties of a linear transformation. The first one is here, the second one is there, the third one is here. And I insist that you need to remember the property number 4. The property number 4 says that if V is a linear combination of the vector V1 up to Vn with the coefficient C1, C2, Cn, then T of V will be again a linear combination of P, V1, P, V2, P, Vn with the same coefficient C1, C2, Cn like here. And we can apply that for the case here. Suppose that P from R3 into R3 is a linear transformation, so that P of E1 to be that, P of E2 to be that one, and P of E3 to be that one. And I recall that E1, E2, E3 three vector with coordinate like that. They are the standard basis for R3. Then you are required to find P of that vector. Then it is very easy because that vector equals 2 times of E1 plus C times of E2 minus 2 times of E3. That one is a linear combination of E1, E2, E3. And we know already the T, E1, E2, E3. Then that is completed by the formula in the previous by using that one. And then the result is here. So that is very important things because we need only to know the value of any linear transformation on a basis. If we know that, we know the whole transformation. And the next one is here. If A is an n by n matrix, given by that thing. Then the function t like that will be a linear transformation from Rn into Rn. And if you look at the matrix multiplication, you will see if we take A and multiply to a vector inside Rn, the result will be a vector inside Rn. So it means that T is exactly a mapping going from Rn into Rn by the formula here. And it is claimed the mapping here is a linear transformation. And today we will see that any linear transformation will be of this form, nothing more. So what we need to know, that is only how to multiply two matrices together, and then we can do anything. And an example for that is what we know already in the high school, that is rotation. Fact one, the rotation by angle theta will be a linear translation T from R2 into R2. And it is given by a matrix like that. And anything here has been explained clearly for you last week. Also, here is another example. That is a projection in space, in R3. The projection on the XY plane, is given by a matrix like that, and it is that is quite familiar to you. And the next one, that the example number 9 here is not familiar to you, but however, it is still a linear transformation. That is a mapping going from M by N into M by N. Please pay attention to the subscript here. It going from the space of on M by N matrix into space of M by N matrix. That is because the mapping make transpose of the matrix, then the number of rows now becomes the number of columns, and the number of columns now becomes the number of rows. So that will be the mapping going from here to there. And it is claimed that this mapping is also a linear transformation. And then we consider the notion canon of a linear transformation. Let T from V to W is be a linear transformation. Then the set of on with the V satisfying that will be called the canon of T, or even we call it Hadnian of the mapping T. And it is denoted by that, or the canon of T to be that one, if you want to see by the formula. And the examples we have. The first one is here about zero transformation. That one is identity transformation. Then the canon will be only zero meter. And the case for the case of the projection like that is previous. Yeah. In this example, we have a projection here. Then the canon of that will be is exactly Z basis, that one. Or we can write it the canon of Z to be that one. I tell you the canon of a linear transformation, the name is new, with the notion is not new. Why that? Because if you consider the case Tx is given by a matrix A like that, and if you are required to find the canon of T, then the canon of T will be that one. And if you look at that, the kernel of D is exactly the solution space of homogeneous system of linear equation like that. And you know already how to find the solution space of a homogeneous system of linear equation. So that is why I say kernel new name, the notion behind the name is not new. And then we claim that the kernel of a linear transformation D is always a subspace of the domain. And sometimes we call it the null space of D. And I repeat, in case D is given by the formula A multiplied by X, with A to be an M by N matrix, then the kernel of D is exactly the null space of A. That? And opposite to the notion of kernel, we have the name, we have the notion of range of a linear translation D. Let D from V to W is a linear translation. Then the set of all vectors inside the codomain so that they are image of some vectors inside the domain. We become the range of D and denote it like that. And you are going to see that even that name, the name is new, but the notion behind the name is not new. And it is here. In case D is given by the formula like that, that is P of X equal A multiplied by X, which A is a matrix, then the range of D will be the column space of A. And the column space of A we studied already several weeks ago. Then after that we try some more new notion. But however, the new notion here is, you know already, you studied already 2 weeks ago. The first one, for a linear translation D from V to W, we define the range of D. That is the dimension of the range of D. And the nullity of linear translation D will be defined to be the dimension of the kernel of D. So you know, given a linear transformation D, we have kernel in the domain and the range in the codomain. The dimension of the kernel will become the nullity. The dimension of the range will become the rank of D. And you know, in case D from Rn into N given by a matrix Ax like that, then the rank of D also is the rank of a matrix A. And the rank of a matrix A, we know already how to find it. And also the nullity of D equal the nullity of the matrix A. And that we also know already how to find. And obviously, because the rank and the nullity of a matrix can be related to each other, then the rank and the nullity of a linear translation D will be related to each other by 0. The formula is here. Or in other words, we can say the dimension of range of D plus the dimension of the kernel of D will be equal to the dimension of the domain. And after that, we define the notion of one-to-one and onto mapping. One-to-one and onto mapping. I will not repeat it here because that I explained to you at least twice last week. And here we say, in order to find a mapping to be one-to-one, it is not so easy. It costs you a lot of calculation. But however, in case of a linear transformation, it is very easy to find it because in that case, T will be 1 to 1 if and only if kernel of T consists of only 0 vector. And on the other side, if you want to verify a linear translation to be onto, it is not so difficult. It will be onto if and only if the rank of T is equal to the dimension of W, or the dimension of the range equal to the dimension of the codomain. And the next one, we can compare one-to-one and onto mapping. One-to-one and onto mapping, it looks like some kind of opposite notion. But however, in case of a linear transformation, sometimes they are the same, they coincide with each other. That is the following case. Suppose that n from V to W is a linear transformation, and we suppose that the vectors for V and W has the same dimension n. Then, in that case, the T is 1 to 1 if and only if it is onto. That is in the case of a linear translation between two vectors like having the same dimension. Then 1 to 1 and onto at the same motion, not different. And here is a suppose. Đây là cái slide cuối cùng trong cái phần review mà các bạn làm tôi cột hừng chẳng muốn nói nữa. We are having 4 matrices in the cases A, B, C, D like that, and we denote it by T, the linear transformation given by those mapping, those matrices A. That is AX equal to A multiplied by X. And then you are required to find which one is 1 to 1, which one is onto, and which one is not 1 to 1 and not onto. And if we remember the definition, it is very easy to work with so many things like that. The first one, look at the matrix A in ABCD here. We find that the mapping T will be going from Rn into Rn. Now we write it. The first one from R3 into R3. The second one, it will go from R2 into R3. That one will go from R3 into R2, and the last one will go from R3 into R3. Then the second column here will give you the dimension of the domain. The domain is here, so the dimension will be 3, 2, 3, and 3. The next, that is the columns here. The next column will be the rank of T. But we know that because T is given by multiplication of matrices like that, then the rank of T equal the rank of A. Fortunately, in our exercise here, all matrices are in row echelon form already. Then it is very easy to find the rank. The rank of, in the first case, because we have 3 non-zero rows, so the rank of A equals 3. So easy. Similarly, the rank of A in the B case will be 2, and here is 2, and here is 2 also. So the rank of T in those cases will be 3, 2, 2, and 2. And now we know that the rank of T plus the linearity of T equal the dimension domain. So it is very easy to see that the linearity of T will be 0 and 0 in the case A and B. But it will be 1 and 1. in the C and D cases. Now, one-to-one. A linear translation will be one-to-one if and only if the scanner consists of only zero vector. It means that the scanner will have dimension 0. Then, the case A and the case B will be one-to-one. And that case C and D is not one-to-one. And the last one, onto. We can see, we need to see that if it is onto or not, then we need to find the dimension of the range and the dimension of codomain. The dimension of the range is exactly the range of T and here. And the dimension of the codomain is 3. So in the first case, it is onto. And the second one, the range of T is the dimension of the range is 2. But here the dimension of codomain is 3. So in that case, it is not onto. And so we can continue it that way. The range of T here is 2. But here the dimension of the codomain is 2. So in that case, the mapping is onto. And the last one, the range is 2, but the dimension of the codomain is 3. So the last case is not onto. So we just only to make a table like that, we see you can solve any exercise in that thing. So that is all what we studied last week. And we begin from this point. So today we continue our study about linear transformation. We already studied one-to-one and onto. Now the other one is one-to-one and onto at the same time. One-to-one and onto at the same time will be called isomorphisms. Isomorphisms. That is it. The name is here. A linear transformation T, which is one-to-one and onto at the same time, will be called isomorphisms. And in that case, the vector space V and W will be called isomorphic to each other. Isomorphisms and isomorphic in Vietnamese we say đặt cấu. And in the name isomorphism, in the name đặt cấu, we have the word đặt. It means bằng. So isomorphism means it equals each other in some sense. Nó bằng nhau theo một nghĩa nào đó. And we have an observation that two vector space V and W will be isomorphic to each other if and only if they have the same dimension. If and only if they have the same dimension. And it will be proved like that. I will omit the explanation here, and it requires you remember about the relation between the rank and the nulity of a linear translation. And it has the homework. I say the homework number 1. We define the mapping F from, in the case A, B, and C. F, that is from R2 into R1, defined by that one. That is, if you look at the plane, that is the direction on the horizontal axis, vector chiều little y. The second one is here, defined by F of x1 equal x1, x1. That is diagonal map. In Vietnamese, it's cảnh sát đường chéo. And the last one, F from R2 into R2, defined by that one. F of x1, x2 equal x2, x1. That is, we exchange the horizontal axis and vertical axis, đổi chỗ trục tung trục ngoại. That is symmetry by the diagonal. Phép lấy đối xứng qua đường chéo. So you are required to verify which one is one-to-one, which one is onto, and which one is one-to-one and onto at the same time. That is, which one is isomorphism. That is your homework. And because we have an observation saying that two vector space will be isomorphic to each other if and only if they have the same dimension. And here is an example for you. The R4, that is the 4 space, has a dimension 4. Now, if you consider M4 by 1, that is space of on 4 by 1 multiplicity. That is a column space having 4 rows. That space also has a dimension 4. And if you look at the M2 by 2, that is space of on square matrix of order 2. That also has a dimension 4. Or if you consider space of on polynomials of degree 3 or less, that also will have dimension 4. And the last one is here. That is the subspace of R5, with the last coordinate is always 0. And here A, B, C, D, and E, 3 cases, 5 cases. That is the 5 different vector space. All of them have dimension 4, so they are isomorphic to each other. Now we are going to come to the main point of the lecture number 6. That is the matrix for a linear transformations. Suppose that we are given a linear transformation T from R3 into R3. T can be given by 2 different ways. The first way, it can be given by a formula like that. T of x1, x2, x3 equals 0. But also, it can be given in the form of a matrix multiplication like that. T of x equals A multiplied by x. In that case, A to be that matrix. And if you multiply that, you will get nothing. So, we have 2 different ways to describe a linear transformation. So why we need 2 different kinds? People prefer to use matrix form of a linear translation. Why that? Because it is first it is simpler to write, because usually you need only to write that one. You don't need to write that thing. It is simpler to read, obviously, but most importantly, it is easily integrated into an algorithm for computer. So that is the reason why people want to write any linear translation into the matrix form like that. The first one is that thing. Now we consider only linear transformation from Rn into Rn. In that case, we have the name standard wedges for a linear translation. Let T from Rn into Rn be a linear mapping. And we write T of E1, we write it, the coordinate column like here. T of E2, the coordinate column is here. And the last one, T of En, will be the coordinate column here. And so what is it? E1, E2, and En? E1, E2, En. That is the standard basis for I. I will not repeat for you what is the standard basis that you need to know already. Now we have N column and coordinate column. We put them side by side. We put them side by side. T1, Te1, Te2 up to Ten. And it makes a wedges like that. And we denote it by A. We denote it by A. That will be an N by N wedges with N column to be here. And we call it standard wedges for T. For T is here. And you can verify that with the wedges A like that, then T of V will be A multiplied by V for any vector V inside I, inside the domain. So now you know what is a standard wedges for a linear translation. The definition is here. And in next few slides, we are going to define a wedges of a linear translation for any vector space, not only in I, not only in standard basis. So that is something we are going to do later on, not right now. Here, that is some explanation for that. So I will give it for you to read. Here is some examples. Suppose that you are given a linear translation T from R3 into R2, and it is given by a formula like that. T of a vector with coordinate x, y, z will be that one. Xong rồi, ba bạn kia trao đổi xong chưa ạ? Xong chưa? Thế sao các bạn cứ để tôi phải chỉ vào tận nơi thế nhỉ? Các bạn chán thì các bạn đi ra đi, đừng làm ồn trong lớp này. So going back to the examples, you are given a linear translation T from RC into R2 by the formula like that, and you are required to find the standard wedges of T. Then, what you need to do, you need to find T of E1, T of E2, and T of E3. E1 is here, E2 is here, and E3 is here. And the formula is here. So, you substitute that into the formula, you get T of E1 to be that, T of E2 to be that, and T of E3 to be that one. Now we have 3 columns, and if we put them side by side, you get that one. The first column is here, second column is here, and the last column is here. So, standard wedges will be that one. So for the simple example, it is very easy to find the standard wedges. You can verify now. If you multiply A by any vector with coordinate x, y, z, you will get that one. And it is exactly the formula in the previous slide. And the last thing here I want to tell you, that is a practical rule to find standard wages. By division, in order to find standard wages, you need to calculate T of E1, T of E2, T of En. Then you need to write columns side by side. But whenever you are given a formula, you can do as follows. The first coordinate here is x minus 2y. It means 1x minus 2y plus 0z. So we take the coefficient 1 minus 2 and 0. We write it in the first column. I'm sorry, on the first row here. It's 1 minus 2 and 0. Now the second coordinate here is 2x plus y. It means 2x plus 1y plus 0z. Once again, we take the coefficient 2, 1 and 0, and we write it in the second row here, 2, 1 and 0. So if we look at the coordinate here, we take the coefficient, we put it here. That is exactly the standard wages. Any linear transformation, you can apply it for any linear transition T from Rn into Rn, if you are given by the formula. Now the next, that is the examples. You need to find, first you are given the projection from R2 into R2. That is the first mapping in the homework I give you. The projection on the x-axis, then that is dxy equal to x, 0. Then the standard wages of that will be that one. T of E1, T of E2 to be that one. 1, 0, 0, 1. So you get nothing. And you can verify that standard wages for the zero transformation will be 0 wages. And the standard wages for the identity transformation is always the identity wages and n of the same order n, like the dimension of the vector space. Now it is your second homework. We go back to 3 mapping given in the previous homework. The mapping you know already. Now you are required to find the standard wages for those mappings. Obviously, the previous slide will help you to do the first things here. Then you need to do this second and the third exercise only. Next, we go to the composition of 2 mapping. That we explained to you already last week, and also composition of 2 mapping, 2 function you know from high school hàm hợp. Các bạn biết từ phổ thông rồi. So composition of 2 maps we studied last week, and now we see. Suppose that we are given a linear transition T1 going from Rn into Rn, and then we have another linear transformation T2 going from Rn into Rp, like that. Then we can compose T1 to T2 with get the new one is T. And you notice T by T2 opposed to T1. Now the domain of T will be the domain of T1, and the codomain will be the codomain of T2. That is, we know already. Then, suppose that both T1 and T2 are linear translation, and I suppose that standard matrix of T1 will be A1, of T2 will be A2. Then we have two things. The first one, it says that the composition is also a linear transformation going from Rn into Rp. What's the second one? Now the standard matrix for the composition will be A2 multiplied by A1. Once again, you need to pay attention to the order of A1 and A2. You cannot exchange A2 into A1. In the composition, you need to write T2 before the T1. You need to write T2 and then T1. Then, here in the matrix, you need to write A2 before A1. That is the standard matrix for the composition of two mapping, T2 and T1. And here is some explanation for you. You can verify it. From the definition, you need to find the T of E1, E2, En, and then apply that one. So I will not go into the detail for that here. And what I want to insist, so you need to pay attention to, that is, in general, T1 composed T2 is different from T2 composed T1. It's different from T2. And here, suppose that you are given T1 and T2, both of them are mapping from R3 into R3. And suppose that they are given by the formula like that. And then you are required to find the standard matrix for the composition T1 composed T2 and T2 composed T1. How to do it? The first one, you need to find standard matrix for T1. And as I told you, we look at the coordinate is here. The first coordinate is 2x plus y. It means that it is 2x plus 1y plus 0z. So the first row of standard will be 2, 1, 0. And the second coordinate here is 0. It means 0x plus 0y plus 0z. So here is 0, 0, 0. And here is x plus z. It means that 1x plus 0y plus 1z. So the last rows of standard matrix will be 1, 0, 1. So that is A1. And A2 can be found by the same way. A2 to be that one. So we have two standard matrices for T1 and T2. Now we compose them together. Then standard matrix for T2 composed T1 will be that thing. If we multiply them together, you get that one. On the other side, if you find standard matrix for T prime equal to T1 composed T2, you get that one. And you look, two matrices are quite different. So it means that T1 composed T2 is different from T2 composed T1. The next, that is inverse linear transformation. Inverse mapping, I explained to you from last week already. Now we go into the case when T1 and T2, they are linear transformation. And If T1, T2 like that, and they satisfy T1, T2 compose T1 equals identity and T1 compose T2 equals identity, then T2 will become the inverse of T1 and T1. In that case, T1 will become invertible. Invertible in Vietnamese, khả nghị, ánh sáng khả nghị. The inverse of T2 ánh sáng ngược của ánh sáng T1. Then, in case the transformation T is invertible like that, then the inverse will be unique, and because that is always denoted by T to the power minus 1, and we call it the inverse of T. Now, I go to the observation. Let T from Rn into Rn be a linear transformation, and I suppose that standard basis of T to be A. Then the following claims are equivalent to each other. The first one saying that T is invertible. The second saying that T is an isomorphism. And the last one saying that the matrix A is invertible. It means that T is invertible if and only if T is isomorphism. If and only if A is invertible. That is observation here. And if one remark, we can see that if T is invertible with standard matrix A, then the inverse matrix T minus 1 will have standard matrix A inverse. Then standard matrix of T inverse will be A inverse. So the inverse of a linear transformation will give you the inverse of a matrix. Right. And here is some examples. Suppose that T is given by a formula like that, and you need to show that T is invertible, and you are required to find the inverse of T. How to do it? Now we write it in the formula. We need to find standard matrix for T. And once again, if we look at here, I use the formula for the first coordinate, second coordinate, and last coordinate to write the first row, second row, and last row of the matrix A. So we don't need to do any calculation. We can find the standard matrix here. We get that? Okay. So the standard matrix for T, we know already. If you want to know T is invertible, you need only to show that A, the matrix A is invertible. A is invertible if and only if it has non-zero determinant. So it's very easy for you to know now. But more than that, because we are required to find the inverse, so we need to find the inverse of A. To find the inverse of A, we write A, and on the right side of A, we write identity matrix here. And applying Gauss-Jordan elimination, we transform it into that one. Then that part will be A inverse. A inverse to be that one. And it is exactly the standard matrix for T inverse. That is now. You can verify T inverse of V equal A inverse multiplied by V. And if we multiply that, you get T inverse of x1, x2, x3 will be that. That is the formula for the inverse method. And the next one, so up to that point, we know anything about the standard matrix of a linear translation from n into n. Now we consider the general case. The general case, that is the case when the domain and codomain, they are vector space of finite dimension. Any vector space, not only Rn or I. That is any vector space. And we suppose that B is a basis for V and B prime is a basis for W. And in order to find the matrix, we need to specify B consisting of the vector V1, V2, Vn. And now if B from V to W is a linear transformation, then we need to find T of V1, T of V2, and T of Vn. The first one, T of V1. T of V1 lies in the codomain. And because the codomain has a basis B prime, we can find the coordinate of T V1 relative to the basis B prime, and we get the color. That is the coordinate of T V1, but relative to the basis B prime of the codomain. We do the same things for the V2. We find, first we calculate T of V2, and then we find its coordinate relative to the basis B prime, again the basis B prime in here. And so on, we continue with the same way up to T of Vn, and we realize the coordinate of that relative to the basis B prime. So by this way, you get n columns. And once again, we put them side by side. Then the m by n, which is having n columns, to be that one. Here, A will be that one. Now I put them together. And that will satisfy T of V prime equals A multiplied by V. That is correct. That is true for any vector V inside V. And then the matrix A, like that, will become the matrix of the transformation T. Now, relative to the basis B and B prime. So in that case, you should remember that. First, we need to fix the basis B on the domain and the basis B prime on the codomain. And the matrix depends on both basis B and B prime. Because of that, we say A is a matrix of the transformation T, but relative to basis B and B prime. That is the definition. In the case of standard matrix, it is very easy because on the domain and the codomain, we take also the same standard basis. But here on domain and codomain, we have different basis B and B prime. Because of that, it requires you to remember how to find the coordinate of any vector according to relative B or relative to B prime. So that is something we need to study, and now we take a short break before going further.
Ôi, ông là ông Nam mà đăng lên Facebook của đăng lên YouTube của ông là ông Nam đăng lên YouTube của cảm ơn ông. Giờ như bài quay của ông là
em hôm qua video sinh em chưa đăng lên à?
ngày quay
Mà em vẫn còn điện thoại trong điện thoại đúng không? Mai xong hôm nay về em đăng lên nhá.
vâng.
Chúng ta học tiếp ạ. Các bạn từ từ để chúng ta học tiếp ạ. So, before the break, we study first standard weights for any linear translation from Rn into Rn. Then we change into general case. We consider any linear transformation from a vector space V into a vector space W. In that case, we need to fix a basis B on the domain and a basis B prime on the codomain W. And then we define the matrix. We define the matrix of T relative to the basis B and B prime. And that one is example for you. That is very simple example. Mời bạn mặc áo trắng trả lời tôi đang nói cái gì ạ? Em cầm điện thoại ạ. Em nhé, đứng lên. Em đứng lên. Em không cần học không ạ? Nếu em không cần học em đi ra ngoài, em đừng có vừa nói chuyện xong rồi lại quay xuống bạn ở đằng sau em nói chuyện nữa. Còn nếu cả mấy bạn đấy cùng không cần học, các bạn có thể đi ra ngoài. Em ngồi xuống đi ạ. Đừng làm những chuyện như thế. So we consider now T a linear transformation given by a formula like that. Obviously, for T, it is very easy to find standard matrix because the formula will give us the standard matrix. But now you are required to find the matrix of T but relative to the basis B to be Z1 and B prime to be Z1. If you see, if you take a look at here, B prime will be a basis for the codomain. Z1 is a standard basis, but the basis B for the domain is not standard basis. How we can find it? How we can do it? Now, you can do it step by step. The first one, T of Z1 equal C0. But C0 now is C time of Z1. 0 time of Z1. And T of minus 1 will be. Then you get T of the first vector here, which is coordinate in B prime will be Z1. And T of the second vector here, which is coordinate in B prime to be Z1. Then the matrix of T relative to B and B prime will be Z1. So we put the column side by side again. So that example is very easy. That example is very easy. We consider the next one. Suppose that we continue with the example in the previous slide. That is, we continue with the mapping here with the matrix we calculate here already. And you are required to find P of V. And V here is a vector 2, 1 inside here. And you need to find T of V using the matrix A we find already in the previous slide. How we can do it? Now because of V equals Z1 and it is exactly 1 time of Z1 and minus 1 time of Z1. That is V. That is because on the domain the basis B to be Z1. The basis B is the domain to be Z1. So the coordinate of V relative to the basis B will be 1 minus 1. So that step is just a little complicated for you. You know already how to change the coordinate. You know how to change the coordinate from the basis to another basis. And then you apply it here to get the coordinate of V relative to a new basis B to be Z1. And if you know that, then you can using the matrix A in the previous slide to find T of V. Then T of V with the coordinate is relative to B prime will be A multiplied by V, B, and it is that one. So the coordinate of that will be and that is T of V to be that one, C time of that plus C time of that, and or you can, that is in coordinate is the basis B prime to be the standard basis. And you can verify again. If you apply the formula in the previous slide, you get that one, and it is exactly here. If you using our calculated which is A. So I summarize for you that the matrix of T relative to the basis B and B prime, how to get it. Suppose that T like that, B is given by that one and B prime given by that one. And vẫn tiếp tục ạ. Sao vậy ạ? Bạn có gì thắc mắc không ạ? Tôi rất phiền lòng ạ. Tôi đã nói rồi, nếu như bạn không thích học môn này, bạn có thể đi ra ngoài, tôi chả phản đối gì cả. Nhưng bạn ngồi trong lớp và bạn cứ nói chuyện với bạn bên cạnh là tôi không thích. Bây giờ tôi có một câu hỏi với bạn. Bây giờ bạn sẽ giữ trật tự hay là bạn sẽ để tôi yêu cầu bạn ra khỏi lớp? Bạn muốn thế nào? Hoặc là bạn tự ra? Bạn làm đi ạ, chọn đi ạ. Bạn chỉ chọn một trong ba thứ đó thôi. Bạn còn nói chuyện một lần nữa tôi sẽ trực tiếp yêu cầu bạn ra khỏi lớp. So, I summarize for you the basis of T relative to the basis B and B prime. We choose B, the basis is the domain, B prime, the basis is the codomain. I specify the vector in the basis B and B prime like that. Then the basis of T relative to the basis B and B prime is following one. You get T of V1 and we take the coordinate of that relative to the basis B prime. T of V2 with the coordinate relative to B prime. And so on, we take up to the T of Vn coordinate according to the basis B prime. And then it's obviously the basis of sine n by n. And that will be the basis of T relative to the basis B and B prime. And in that case, what I want you to remember, that is the formula here. The T of V relative to the basis B prime will be A multiplied by the coordinate of V relative to the basis B. Yes, B and B prime to be 0. And that formula is correct for any vector V inside the domain. Now I want you to pay attention to the special case, that is the case when domain and codomain are the same. In that case, usually we choose the basis B, the same basis on both domain and codomain. And because on domain and codomain have the same basis, we need to say that the matrix of T relative to the basis B. We don't have to say relative to the basis B and B prime because now we have only one basis on both sides. And the example is that in case T from V to V is identity transformation and any B is any basis for V, then the matrix of T relative to the basis to any basis B is always identity matrix. You can verify it by yourself. Because it is the identity, so the matrix is always identity matrix. The last part of the chapter number 6 is transition matrix. Ma trận chuyển cơ sở, once again. And similarity in Vietnamese đồng dạng, ma trận đồng dạng. Once again, the name is quite new, but it is not so difficult to follow. Now, I suppose that in this section, in the section 6.4, we consider only linear transformation D from V to V. That is, only in the case domain and codomain are the same, and we are going to choose the basis B on both sides. Then, suppose that we fix a basis B for both sides, for domain and codomain is here. Then, the basis of T relative to B will be that one. We need to compute T of V1, T of V2, and T of Vn, and we write the coordinate column relative to the same basis B, and A is formed by putting the columns side by side like that. That is the basis of T relative to B, and obviously that one is a square basis of side n by order n. And we have that one. Because of that, so we have T of V B equal A multiplied by V relative to B. That you know already in the previous line. That is what I require you to remember. Now, suppose that we are given another basis B prime. We have the same number of vectors inside. Say B prime to be W1, W2, up to Wn. That is another basis for V. Then, the matrix of T, but relative to basis B prime, will be the following. A prime will be formed by T of W1, T of W2, and T of Wn. And find the coordinate relative to the same basis B prime. That is the basis of T relative to B prime. And now, with that, we have the following. Then, with that, we have T of V relative, the coordinate of T of V relative to B prime will be the matrix A prime multiplied by the coordinate of V but relative to B prime. So we have two different formulas according to two different matrices A and A prime. Now I call P by that. So please remember, that one is a transition matrix from B prime to B. Mà chạy chuyển từ cơ sở B phải sang cơ sở B. With that, we have the following things. Then, the coordinate of V relative to B will be P multiplied by coordinate of V relative to B prime. And if we take transition matrix from B back to B prime, we get the P inverse, or by intuition, it is that one. So once again, it requires you to remember what is the transition matrix from B prime to B, from B to B prime. Then, with P inverse, you have that one. So if you look at the slide here, so many formulas for you to remember. But however, you can look at that one. The picture here will give you. The first one here, you have the coordinate of V relative to B prime, and using T, you transform it into T of V. You find the coordinate of T of V into B prime. And in order to get that, from here, you need to apply the matrix A prime. That is, the last row here is exactly that formula. And the top row here, from V, the coordinate of V relative to the basis B, up to here, the coordinate of T, V relative to B. we can use that formula. And from here up, that is, you change from the coordinate of v related to b prime into the coordinate of v related to b. That is the first one. That is the first one. Then you apply that formula. And so on. That you get the formula here. So on the slide show you that picture. That picture. You go from here to there by using that way. That is what we say here. We have two ways to get from v, the coordinate of v related to v prime, to the coordinate of tv to v according to v prime. The first way, we call it the direct way. The direct way, that is, we go by the down arrow here. And the indirect, that is the direct way. The indirect way, that is here. We go first from here to there, and then go from V to V by A, and then go back to that way. Then, because that is the same thing, so we get the formula here. Or I require you to remember, from here you get A prime equals P inverse multiplied by A multiplied by P. So I summarize two slides. Two slides show you, if you are given only one linear transformation T, but you consider two different bases, B and B prime, on the vector space V. Then the linear transition T is given by two different matrices A and A prime. And A prime will be related to each other by the formula here. And that will be very important later in the next lecture, in the next chapter. A và A phẩy là hai cái ma trận của cùng một ánh xạ tuyến tính, nhưng trong các cơ sở khác nhau. Chúng nó liên hệ với nhau bởi cái công thức nằm trong cái khung đỏ như thế này. Trong đấy cái ma trận P rất quan trọng, nó là ma trận đổi cơ sở từ P phẩy sang B. Here is an example. Now suppose that you are given a matrix, a linear transition P from R2 into R2 by that, and you need to find the matrix of matrix A prime for T, but now relative to the basis B prime. And obviously B prime here is no longer standard basis, no longer. Then the first way, the first method, you can use definition. You need to find T of the first vector, T of second vector, and we find the coordinate of that relative to B prime. And then you get T of that equal to here. And the coordinate column will be that one. The second will be here. And because of that, the A prime will be that one. You put column by column. The second way, first we find standard matrix for T to be that one. Very easy because we know that. So the standard basis will be 2 minus 2 and minus 1, 3. It is 2 minus 2 and minus 1, 3. The next one, you need to find transition matrix from B prime to B, and it is also very easy to find because it is here. Then A prime, now the last step, A prime equal P inverse multiplied by A multiplied by P. P inverse to be that one, so A prime to be that one. And once again, you can verify The reason here is exactly the A prime we found in the previous slide. The next example for you is, suppose that you are given the basis B like that and B prime like that. There are two different bases for R2. And suppose that we know already A to be the basis for B relative to the first basis here. And you are required to find the basis of T, but now relative to the second basis B prime. Now here, none of them are standard basis. Then obviously the best way, that is, you need to find transition matrix. That is very easy in case small dimension like that. Then transition matrix B. First we find transition matrix from B prime to B to be Z1. Then A prime transition from B to B prime will be Z1. That is the way to find B inverse is very easy to find. Then A prime will be B inverse multiplied by A multiplied by B to be Z1. So that is, in case of small dimension, it's very easy to find, to do calculation. Even when you get the dimension up to 3, it is very easy to find the transition matrix. If you remember the formula to find transition matrix, and the last step, you need to multiply 3 matrices together, you get the A prime. Now, suppose that you did already the exercise in the previous example. You know that A, you know A prime. Then you are required to find the V of B and PV of B, and that is something, some kind of exercise. Now it is very easy. If anything we know already, the coordinate of V relative to B to be Z1, and then T of V relative to B equal A multiplied by V. The coordinate of V according to B, and you get Z1. And if you do it with the coordinate, with the basis B prime, you get Z1. So Z1 and Z1, they are the same vector, but the coordinate in different bases. You can verify anything here. So I go to the notion similar matrix or matched from that. Two matrices A and A prime of the same square matrix A and A prime of the same order n will be said similar to each other, or we say A similar to A prime if we can find an invertible matrix P, so that A prime equal P inverse multiplied by A multiplied by P. So now we see two matrices will be similar to each other if and only if they are matrices of the same linear transformation, but according to different basis. Hai ma trận vuông sẽ đồng dạng với nhau khi và chỉ khi chúng là ma trận của cùng một trận định tính trong các cơ sở khác nhau. That is the reason why they define similar matrices here. Now we have the following claim. A matrix A is always similar to Isn. It's very easy. If A is similar to B, B is similar to A. And if A is similar to B and B is similar to C, then A will be similar to C. That is some property of similarity. The explanation for 3, fact here is given here. I need it for you to read by yourself. Now, the similar matrix A and A prime, here is an example. They are similar to each other because for if you take P to be like that, then you get A prime equal P inverse multiplied by A multiplied by P. That. And the next one, the same things like that, you can verify with P to be that one. And we can compare two matrices for the linear transformation. Suppose that A is a transformation of P relative to standard basis. Then the matrix for T relative to B prime. We know already in the previous, in some similar previous slide, they must be similar to each other. That is, if we find P to be the transition matrix from B prime to standard matrix, then P inverse will be that one, and A prime will be that one. Will be that one. You can verify it, and then A prime and A they are similar to each other. And the last point about the similar matrix is following. Now we consider the case D to be a diagonal matrix like that. Then, if we take the power K of D, what do you get? If we multiply D by D by D K times, you will get that one. D to the power K will be again diagonal matrix. The entry on the diagonal will be the power K of D1, D2 up to Dn. That will appear in that kind of exercise will appear in the next chapter. When going to that, I will point to you. And with the diagonal matrix, the transpose is nothing changed. And D inverse will be that one in case all the entry lying on the main diagonal are non-zero. So that is anything we need to study during the chapter number 6, and we go right now to the lecture number 7. Xin lỗi các bạn, 1 phút nữa. So the lecture number 7, that is, once again, we go back, eigenvalue and eigenvectors. But mainly, the lecture number 7, we study about diagonalization. So, we have diagonal means đường chéo. Diagonalization means chéo hòa. That is, suppose that we are given a square matrix, we try to make it becomes a diagonal matrix. Cho một mã trận vuông cố gắng làm sao để biến nó thành một mã trận. đường chéo. Why we need the diagonal wedges? Because before, so at the very last slide of chapter number 6, we know the convenience of a diagonal wedges. Cái slide cuối cùng của cái chương trước chúng ta vừa nhìn thấy là cái ma trận đường chéo rất thuận tiện. It's very convenient in calculation. So that is the reason why we want to do diagonalization of any square wedges. Anyway, we go. So for the serial first slide, just only repeat what we studied already. Suppose that A is a square matrix of order n. Then the eigenvalue is following. We want to find a number lambda so that together with lambda we can find a non-zero vector in Rn. Satisfying A multiplied by x equal lambda time of x. If we can find lambda and x like that, the number lambda will become eigenvalue. And the x, the vector x, the non-zero vector x, satisfying that will become the eigenvector corresponding to the eigenvalue lambda. And here is a geometrical interpretation for that. X to be like that, ax equal lambda x, like that. Then lambda x to be here. The examples is following. A to be square matrix like that, x1 and x2, that is the two unit vectors on the horizontal axis and vertical axis. Then we have A x1 to be that, and with that you see that will be eigenvector and the number 2 is eigenvalue. So that vector is eigenvector according to the eigenvalue 2. And on the other hand, if you take A x2, from here you get that is an eigenvector, but now the eigenvalue will be minus 1. So that eigenvector will be corresponding to the eigenvalue minus 1. So for A, we have two different eigenvalue, that is 2 and minus 1. And each eigenvalue will have an eigenvector. Now that one is a new one. New, not new. The new one is, we say that, suppose that A is a square matrix of order n, and lambda is an eigenvalue. Then the set of all eigenvector of lambda together with zero vector will be a subspace of I, and that subspace will become the eigenspace of lambda. Please remember that eigenvector must be non-zero. So we need to add zero vector to make it become sub-vector space. If you want to make something to be a vector space, please remember that the vector space always contains the zero vector. So here we need to add zero vector. And the explanation is here. Once again, in order to prove something to be a subspace, you need to verify property number 1 and property number 6. Two properties, no more. And here is an example. Given A to be like that, you need to find eigenvalue and eigenspace. That. Now before, I mean, some weeks ago, we studied already the eigenvalue and eigenvector, we know how to find that. But now, more than that, we are required to find eigenspace. Then, the first one, you see, by definition, if V has coordinate x and y. We multiply a to v, we get that one. X, y, we begin minus x and y. Then, for a vector, now, if we consider a vector lying on the horizontal axis, that is x0. Then multiply by that, we get minus x0. That is minus 1 multiplied by x0. It means that minus 1 is one eigenvalue. That is eigenvalue. And the second one, for any vector lying on the y-axis, that is here. Then if we multiply them together, we get 1 multiplied by that vector. It means that 1 is eigenvalue. So the matrix has two different eigenvalues, minus 1 and 1. And if you look at by a geometrical way, multiply a vector x, y by R2 by the matrix A will give us a reflection on the vertical axis. Nhưng cái mặt trận A với một vector xy thực chất là tôi lấy đối xứng y trừ y. Then the eigenspace corresponding to lambda 1 will be the x-axis and the eigenspace corresponding to lambda 2 is y-axis. On here, on the x-axis, that will be z1, but on the y-axis, nothing changed because if you take the point here, if you take the reflection, nothing changed because it is lying here. Nếu các bạn lấy một vector hay là một điểm nằm trên trục y và lấy đối xứng qua chính cái trục y, đấy có nghĩa là nó không thay đổi gì cả. Nhưng lấy một điểm nằm trên trục hoành thì nó sẽ sang cái điểm đối diện vẫn là trên trục hoành nhưng nào bên đối diện. So that is the geometry for the exercise here. Now, suppose that A is a square matrix of order n. The eigenvalue of A will be a solution for that one. That one we know from several weeks ago. That is the way how to find the eigenvalue and how to find the eigenvector. In order to find the eigenvalue, we need to write determinant of lambda I minus A equals 0. That has been characteristic polynomial, characteristic equation. And the eigenvector of A will be the non-zero solution of the homogeneous system of linear equation, lambda I minus A x equals 0. So that is what we know already. And that one is homogeneous system. And lambda x equals 0 has non-zero solution if and only if determinant of that equals 0. And because of that, lambda must be the solution for the characteristic equation here. And here I just only repeat some name for you. Now, suppose that we are given A and you are required to find eigenvalue and eigenvector. That you know already, so I go very fast here. Characteristic equation to be Z1 and value, eigenvalue will be minus 1 and minus 2. And then in order to find eigenvector, we need to solve the system of linear equation to be Z1. And solving it, we get the solution set to be like that because eigenvector must be non-zero, so we always require that P is non-zero. Similarly, for lambda 2 equals minus 2, the eigenvector will be found by solving the system of linear equation, and you get that one. And once again, we require that P is a non-zero. So anything here we studied already some weeks ago. and you can verify again that. Now, you need to find eigenvalue and eigenvector for the matrix A. And then after that, you are required to find the eigenvector, the dimension of eigenspace. Now, that requires you to do some more things. That is, how about deal with the eigenspace? Then, the first one, you need to write characteristic equation like that. Then, with that, we have only one solution. That is lambda equal 2. Lambda equal 2. Then, now we need to find the eigenvector corresponding to lambda equal 2. We solve the system, that's the homogeneous system of linear equations like that one. And we get the solution like that. With that, you see the eigenspace will have dimension 2 because it has eigenspace of A with corresponding to lambda equal 2 will be that one. It has basis consisting of two vectors, that and that, so the dimension is 2. And because of that, the dimension of eigenspace will be 2. So at least today we begin the lecture number 7. We repeat the eigenvalue, eigenvector, and we study the new one, that is eigenspace. But however, eigenspace is nothing new. It is once again the solution space of a homogeneous system of linear equations. And you know how to find the basis for that, how to find the dimension. And the next one, next week, we will finish our course on linear